Welcome to Solids and Liquids. In this new unit, we're going to be learning about intermolecular forces, properties of liquids, types of solids, semiconductors, and even types of alloys. But let's get started today with intermolecular forces. Here we go. So the first thing we're going to talk about is intramolecular forces versus intermolecular forces. Intramolecular forces, that's what we've been talking about this whole year. These guys are bonds, like the bond between oxygen and hydrogen in water. An intermolecular force, on the other hand, is a force of attraction between two molecules. That would be between the hydrogen of one water molecule and the oxygen of another water molecule. So intramolecular forces, bonds, intermolecular forces between two different molecules. The first type of intermolecular force, or IMF, that we're going to talk about are ion-ion attractions, otherwise known as ionic bonding. That is the attraction between oppositely charged ions, such as in sodium chloride or salt. So sodium is a normal atom with 11 protons and 11 electrons, and chlorine has 17 protons and 17 electrons. But in order for sodium to obtain an octet, it needs to lose an electron, so it will give one of its electrons to chlorine, so that sodium now has 10 electrons and 11 protons, so a positive 1 charge, and chlorine now has 18 electrons and 17 protons, so a negative 1 charge. And the chlorine ion is larger than the sodium ion because the sodium ion turns into neon, which is 1 energy level smaller. So now these ions are oppositely charged and opposites attract, and they form a lattice of negatives and positives and negatives and positives all right up next to each other because opposites attract. It's like a match made in heaven. So the next type of IMF we have is ion-dipole interactions. This occurs when a soluble ionic compound is dissolved in a polar liquid, such as, for example, salt water. So the ions will have a higher attraction for water than for each other. The positive ions are attracted to the negative end of a polar molecule. The negative ions are attracted to the positive end of a polar molecule. So in this example, we have a positive ion, and notice that it's attracted to the negative ends of these polar molecules, and a negative ion that's attracted to the positive end of these polar molecules. Let's look at salt water specifically. So we have Na plus surrounded by the partially negative oxygen atoms in a water, and we have the Cl minus surrounded by the partially positive hydrogen atoms in water. What happens when you try to dissolve salt in water, or really any ionically bonded thing into water, is that there is a conflict between the ion-dipole intermolecular forces and the ionic bonds, or the ion-ion intermolecular forces. If the ionic bonds are stronger, then the positive and negative ions are pulling together, and the ionic thing, will not dissolve. If the ion-dipole intermolecular forces are stronger, so it's pulling out more than in, then the ionic substance, will dissolve. So that is the interaction that's happening when you're trying to dissolve an ionic substance in water, or a polar substance. Next we have dipole-dipole interactions. This is the attraction between the negative end of one polar molecule and the positive end of another polar molecule. These types of molecules are considered to have a dipole moment. So this is what we're saying, polar molecules that we just got finished talking about. So let's just say, for example, HCl. And so hydrogen is partially positive and chlorine is partially negative, but they're sharing their electrons, so it's one big molecule. And so now the chlorine, which is partially negative, is going to be attracted to the hydrogen, which is partially positive, from another molecule. Molecules that exhibit dipole-dipole interactions can be solids or liquids. So this is a pretty picture of a solid. Notice that it's nice and orderly and organized. And this is a picture of a liquid, which is less organized. In all cases, we have the negatives attracted to the positives and the positives attracted to the negatives. It's just that the solid is more organized and orderly. And in all cases, they need to work to maximize the attractive forces and minimize the repulsive forces. Next, we have hydrogen bonding. Hydrogen bonding is a particularly strong type of dipole-dipole force where hydrogen is attracted to a small and highly electronegative atom, such as nitrogen, oxygen, or fluorine. Specifically, this occurs when hydrogen is bonded to NO or F in one molecule and attracted to NO and F in a neighboring molecule. This can be 5 to 10 times stronger than a typical dipole-dipole interaction. So here we've got hydrogen bonded to oxygen in one molecule and attracted to the oxygen in another. So for example, water. This molecule on the right would not have hydrogen bonding because there is no hydrogen bonded to oxygen or nitrogen or fluorine. Let's look at the hydrogen bonding in these molecules. See, we have a hydrogen bonded to a nitrogen, attracted to an oxygen in a neighboring molecule. Here we have a hydrogen bonded to an oxygen, attracted to an oxygen in a neighboring molecule, a hydrogen bonded to an oxygen, attracted to an oxygen in a neighboring molecule. You also see hydrogen bonding in DNA. Look, here's a hydrogen with a nitrogen, attracted to a nitrogen in another molecule, and a hydrogen with a nitrogen attracted to an oxygen in another molecule. This is what happens when thymine and adenine get together, T and A. And cytosine and guanine, notice you have an NH attracted to an O, an NH attracted to an N, and an NH attracted to an O. So this is the CG. If you want to look at that in your biology textbook, we have the A attracted to the T and the C attracted to the G. Notice here that there are, it seems silly, but only 2 sets of dashy lines because there's 2 hydrogen bonds. But with the CG, there's 3 sets of dashy lines because there are 3 hydrogen bonds in cytosine and guanine. So if we were going to look at dipole-dipole and hydrogen bonding together, dipole-dipole forces get stronger as you go down a group because the atoms are larger and therefore more polarizable. The exception is molecules that undergo hydrogen bonding. So larger atoms are more polarizable. Let me see if I can make that a little bit less bad handwriting for you guys. Okay, larger atoms are more polarizable, which means that at any given point the electrons might be on one side or another, and therefore make the atom have more of a dipole moment. So as you get larger within a group, silicon is the smallest. Well, that's not true. Carbon is the smallest. And then silicon is smaller than germanium, which is small, and then tin, which is large. And so as they get larger, the boiling temperature, which is an indicator of intermolecular forces, gets greater. Notice that the exception is hydrogen bonding. Water and ammonia both have hydrogen bonding because an N is bonded to an H in one molecule and is attracted to an H in a different molecule. So notice that these hydrogen bonding have an exception to larger atoms having greater intermolecular forces. In all cases of dipole-dipole attractions, including hydrogen bonding, potential energy decreases as the molecules are pulled closer together by their IMF. The more polar the molecules, the stronger the IMF. More polar equals stronger IMF. So they have a lower potential energy. energy must be added to weaken or break these IMFs. So here, for example, in water, there is a large electronegativity difference between the hydrogen and the oxygen, and therefore this is more polar. Since it's more polar and has a stronger intermolecular force, there is a lower potential energy. Whereas in this case, and let's just say it was HCl, there is a smaller electronegativity difference between the Cl and the H, so they're going to be a little bit farther apart. They're not sharing quite as, they're sharing more evenly or less unevenly, and so they have higher potential energy. Alright, the next one we've got is dipole-induced dipole attractions. In this case, these are attractions that occur when a polar molecule induces a dipole in a nonpolar molecule. The polar molecule attracts the electron density of the nonpolar molecule to its positively charged end, which induces a temporary dipole in the nonpolar molecule. This is a very fleeting and weak type of force exemplified by, let's say, oxygen or carbon dioxide gas dissolved in, for example, water. The forces become stronger when the polar molecule has a greater dipole moment, or when the nonpolar molecule is larger and therefore more polarizable. In this picture, let's pretend that we have an HCl again with a Cl which is partially negative and a hydrogen which is partially positive, attracted to some nonpolar species, let's just say oxygen or nitrogen. And so the negative electrons might temporarily be attracted to that positive hydrogen, which would then cause the, let's say, left-hand side of this molecule to become negative temporarily. It's an induced dipole because the dipole or polar molecule is inducing or causing a dipole on a nonpolar molecule. So even though it's a nonpolar species, it becomes a polarized molecule. The next one we've got is induced dipole, otherwise known as LDF, or London dispersion forces. Named after Fritz London, not Jack London. These attractions occur between all molecules, polar and nonpolar, but they're most pronounced in non-polar, non-charged molecules. London dispersion forces are very similar to dipole-induced dipole forces in that one molecule will induce a dipole in another. They're caused by Coulombic attractions between temporarily induced dipoles of neighboring atoms or molecules. So, for example, we have these electrons that are kind of floating randomly around this positive nucleus. And at some point, the more electrons you have, the more likely this is to happen. Let's say the electrons end up only on the left-hand side, which will cause the left-hand side to be partially, temporarily negative. And if the left-hand side is temporarily negative, the right-hand side is temporarily positive, which will cause the floating electrons in the next molecule over to be attracted to that positive side, which makes the left-hand side negative in the next one, which will cause the next molecule over have the electrons there attracted to the positive side. And by this time this happens to maybe 2 or 3 molecules, the original molecule is back to being totally normal and not having any dipole at all. So it's a very temporary, very fleeting type of force. London dispersion forces get stronger as the molecules get larger. Stronger when there are more electrons. Because there's more electrons in the molecule, there's a greater probability that an instantaneous dipole can be produced, which will induce a dipole in neighboring atoms or molecules. So if you look down the halogens from fluorine, chlorine, bromine to iodine, iodine is the largest and has the greatest boiling point, which is an indicator of IMF. And fluorine is the smallest, which has the smallest boiling point, which means it has the weakest intermolecular forces. Helium is even smaller than that. London dispersion forces also get stronger as pi or double bonds increase whereas the structure of the molecule allows other molecules to approach more closely. So a large amount of LDF with pi bonds, that is double bonds or triple bonds, and in a straight chain. This molecule to the right is more polarizable because it allows other molecules to get closer to it and it can intertwine. If you were to take the time to count, the molecule on the left and right have the same number of carbons and the same number of hydrogens, but the molecule on the right has a greater boiling point, stronger intermolecular forces, because it can interact with other molecules of the same type better. It's less spherical and more in a line. Let's talk about the relative strength of all of these intermolecular forces, and this chart is kind of upside down from what's in your notes, so that the strongest is at the bottom, and the strongest is actually not written, and that is ion-ion. So ion-ion, or ionic bonding, would have the strongest interactions, because that's full positive and negative charges together. Then comes ion-dipole, which is a mixture of ionic and polar compounds. Then comes hydrogen bonding, which is all polar compounds, but with a great electronegativity difference, which means that they're more polar or closer to ionic. Then we've got dipole-dipole, which is all polar molecules without a huge electronegativity difference. Then we have ion-induced dipole and dipole-induced dipole. Ion, and then I'm just going to write ID, and then dipole-induced dipole. And those are kind of when we have nonpolar molecules attracted to either ionic or polar molecules. And then finally, the weakest we have is dispersion forces, or London dispersion forces, that is nonpolars and nonpolars. Now, in some cases, large molecules with only LDF can actually exhibit greater IMF than polar molecules with dipole-dipole forces or even hydrogen bonding. For example, iodine, which is a nonpolar molecule, is a solid, and water, which is polar and it's got hydrogen bonding, is a liquid, which indicates that the intermolecular forces in iodine are actually stronger than the intermolecular forces in water. That is because iodine is so large, it's so polarizable. So the list that you have in your notes is only a rough guide. It's not an exact everything will be this way all the time. Also, substances with similar types of intermolecular attractions tend to be miscible or soluble in one another because of their similar types of charges or not charges. So let's just look at this chart to see if it will help you kind of organize in your brain what's going on here. This chart is not in your notes. So if you had two polar molecules together, say water and another water, that'd be dipole-dipole forces. If you had two nonpolar molecules, that'd be iodine and another iodine. That'd be induced dipole forces, such as London dispersion forces. If you wanted to mix a polar and a nonpolar, that'd be dipole-induced dipole. If you wanted to mix a polar and ionic, ion-dipole. A nonpolar and ionic, ion-induced dipole. And finally, ions and ions is ions attractions or ionic bonds. Now, the application of this is if I tell you water or HCl or iodine or helium, that you should be able to tell what type of intermolecular forces are in that molecule. So the way that you're going to do that, first you're going to look at the interacting molecules or ions, and are there any ions involved? Is there an Na plus or an NH4 plus? Is there a chlorate or a nitrate? If that's a yes, then is it both polar molecules and ions or just ions? Both of them, that's ion-dipole forces. For example, I've dissolved an ionic compound in water. If it's not, it's only ions, then it's plain ionic bonding. So we have Na and Cl, or NH4 and NO3. Those are all ions. Let's say there's not any ions involved. So they're polar molecules, yes or no? Let's go with yes, there's polar molecules. Is it a hydrogen bonded to an N, O, or F atom? That's a no, then it's just plain dipole-dipole. That's a yes, then it's hydrogen bonding. And if there is no polar molecules, then it's all nonpolar, so it's London dispersion forces. Last thing, and I said this a minute ago, but just to picture to kind of see it, like dissolves like, or similar types of bonding will dissolve in similar types of bonding. Polar dissolves polar anionic because of the opposite charges that are there within the molecule. Nonpolar dissolves nonpolar, probably because of the induced dipole that's hanging around. And then that's it. Join me next time for something else, effects of intermolecular forces. We'll see you then.